Okay, everyone, so in this video, we're going to go a little bit further into our understanding of integrals. And just as when we started talking about derivatives, we first looked at what they meant graphically, which was the slope of a line tangent to the curve. Then we got into more of a conceptual understanding that they were an instantaneous rate of change. Now, if you look at the way we've approached integrals, we've approached them in a very similar manner. We first said, okay, integrals represent an area under the curve. And now, with an understanding of the fundamental theorem of calculus, we are going to understand how an integral also comes to represent a net change. But before we talk about that, I just want to go over a couple of symbols we're going to use to describe some things. So first of all, if we're given a function f of x, you guys already know that f prime of x is a derivative of that function. F double prime of x is a second derivative. We could go on to an infinite number of derivatives if we like to. But if you see capital F of x, we refer to that as something called the antiderivative. And the fundamental theorem of calculus is really what is the relationship between the derivative and the antiderivative. So, in its most simple form, the fundamental theorem of calculus just states this. Okay? Now, this left-hand side of the equation is another way of just saying that if we take the derivative of the antiderivative of a function, we just get the function coming out when we do that. Likewise, it also goes the other way. If we take the antiderivative of a derivative, we just get the function coming back in return. Now, there's another slightly more mathematical, a little bit more complicated way that the fundamental theorem of calculus is illustrated, typically in textbooks, that relates back to the chain rule. But we're going to talk about that in the next video. For now, if you just understand this, that's really the first thing you need to understand what the relationship between a derivative and an antiderivative is. It turns out that they're actually inverses of each other. So just remember that the exponential function and the log function were inverses of each other. So are the antiderivative and the derivative. Or so are, for example, sine and arcsine or inverse sine. They're all just inverses of each other, and all the same properties of inverses work within all of them. So if we go back to the diagram we had before, if you remember what we had on the last slide, which was that if we take the derivative of the antiderivative, we just get the function. If I'm going to do this in two different ways, we're going to do the right-hand side is like taking a derivative, okay? So if we take a derivative of a function, we get the derivative of that function. If we take the derivative once again, we get the second derivative, all right? Now, on this other side, we're going to look at the antiderivative, which I will use as the integral symbol. If we take the antiderivative of a function, we get the antiderivative. Now let's look how we could go back and forth between this. What would you think we would get if, for example, we did the antiderivative of the derivative? Well, if you understand the fundamental theorem of calculus and what we just discussed in that last slide, again, it's just like going backwards. If we took the antiderivative of a derivative, we just get the function again. Likewise, if we take the antiderivative of the second derivative, we would just get the first derivative. Okay? Now, also, just as the fundamental theorem of calculus right here states, if we take the derivative of the antiderivative, we just get the function. Okay? So as you can see with this diagram right here, I like to think of derivatives as going forwards and antiderivatives as going backwards, like they kind of have a direction. You don't need to use forwards and backwards, but it's important that you, at least at this point, understand why I drew these arrows the way I drew them and how you can go, as I said, backwards to basically go down orders of a derivative, or you can go forwards to go up orders of a derivative. All right? So now we come back to the definite integral. You guys have seen this symbol again. But what the definite integral actually represents is when you evaluate an integral, again, you get the antiderivative, that capital F of x. And so an integral of just a function little f of x from a to b is actually equal to the net change in the antiderivative over that same interval. That's why we have capital F of b minus capital F of a over here. Remember, definite integral also gives you a value, okay? But to calculate that value, we need to first calculate the antiderivative. In the next unit, we will actually go into methods for calculating antiderivatives by hand. But for this unit, we're actually just going to stick to calculating antiderivatives using our calculators. The calculator has a built-in function. If you hit the math button and you go down to option number 9, depending on what type of calculator you'll have, you'll either see something that looks very similar to the integral symbol, or you will see if you have like a TI-82 or something like that, you'll see a command that says FN INT standing for, I think it stands for integral function. To be honest, I really don't know what FNINT, why they named it that way. I'm assuming it means integral function or something like that. But anyway, so this is really what a definite integral represents in terms of how you calculate them. Now in the previous units, we've just thought of definite integrals as areas under the curve, which is true. But in this unit, we see that one way to calculate those areas under the curve, as we learned previously, was using Riemann sums or trapezoidal sums or something like that. Well, now we see that if we just calculate what the antiderivative is, we can apply it to this formula as another way to solve what a definite integral is. So, for example, let's solve a particular definite integral using our calculator. If you're going to be using a TI-83 or TI-84 plus or any of those other kind of calculators, this is what you will see when you hit math and then option number 9. And so when you hit that, this is what's going to show up on your calculator when you evaluate that integral. Now, it kind of goes without saying that what you're going to plug into these dotted squares, you're going to put your lower limit of integration in the lower one, your upper limit, or not DEB, your upper limit of integration in the upper one. In this box is going to go the function that you want to integrate. And in this last box, typically you're going to put an x if it's a function of x. However, if you were looking at, say, a function of t and you were using t as a variable, you would plug a t in to that dotted line. But really, using your calculators, there's not much need to do that for this class. Just consider everything as a function of x, and then you'll always be able to solve it. Now, if you happen to have a TI-82 or something older than a TI-83, when you hit math and then 9, you're going to see something that looks like this pop up. And then inside that parentheses, you first insert what the function is. Then you insert the variable x. That's the same as this step right here, basically saying what are we taking the integral with respect to. Then you insert your lower limit of integration, then your upper limit of integration. So right now, again, in future units, we will learn how to by hand calculate antiderivatives. But for now, we'll actually just evaluate definite integrals either by using a Riemann or trapezoidal sum, or if we want to find an exact definite integral, we'll just plug it into our calculator using the FNINT command. So let's look at an example of how to do this. Let's look at this particular integral. So try to pause the video right now and solve what this integral will be using that FNINT command on your calculator. All right, if you give it a shot, well, if you're going to use a TI-83, it's pretty self-explanatory what you plug in. You saw in the previous slide that if you have a TI-83, really that whole definite integral symbol just comes up, and you just match it to what we have right here. Whereas if you're going to be using FNINT, again, you put in your function first, then the variable x because we're integrating with respect to x, then the lower limit, then the upper limit. Then if you did this correctly, you should get that this integral is equal to 48. If you were not able to get 48, try to do it again, try to plug it in, because it's very important that you understand how to use FNINT as we go forward in this class. So, as I said before, the fundamental theorem of calculus, so now we kind of know what this thing called the antiderivative is. Again, it's kind of like the opposite of a derivative, whereas when I say a derivative is like going forwards, an antiderivative is like going backwards. But we also knew that in previous units that the definite integral represented an area under the curve. Well, it turns out that that area under the curve also represents a net change. And the wording that I use right here and this symbology right here is very, very important because a lot of students actually get this wrong. And I'll read it right here and kind of go over how students get this wrong. And that's that the integral or the area under the curve of the rate of change of a derivative. Now, it's very important that you're looking at a derivative in here. Between the limits x equals a to x equals b is equal to the net change in the function. So notice the way I use the wording. If we look at the integral of the derivative, we get the net change in the function, and that shows right here. Here is the integral of the derivative from a to b, and this would be the net change of the function from a to b. Okay? So the biggest mistake that most students make is they say this. The integral from a to b of f of x dx is equal to f of b minus f of a, where everything is a little f. That is not true, okay? We need a rate of change in here to get a net change of a function. Now, see if you can pause the video and figure out what I would actually write here if I did this. All right, if you gave it a shot, hopefully you should have said this would have been the antiderivative of b minus the antiderivative of a, because in this case, the function f of x represents the rate of change of the antiderivative. Okay, so it's very important that you understand these two integrals, which I just put up here, because like I said, a lot of students get tripped up with this when they first start evaluating integrals, or they're first trying to apply evaluating definite integrals to real world sort of problems. So I have an example of a couple of those real world problems here. So the first one is the integral or the area under the curve of a function representing the rate of snowfall in inches per hour from a time t equals 0 to t equals 6 hours represents what? Pause the video and see if you can fill in the rest. Okay, if you give it a shot, really what we're asking for is to evaluate a definite integral. That definite integral would be from t equals 0 to t equals 6, and we'll just call the rate of change of snowfall s prime of t dt. Notice that I keep my variables consistent in here. That's very important that you do that. If you have a function of time, you want to use dt at the end of your integral. If you have a function of theta, you want to use d theta. It's just like when we did derivatives, when you have that d over dx in the derivative, it's what we're taking the derivative with respect to. In this case, it's what we're integrating with respect to. So if we did this, this would give us the net change in snowfall between the hours of t equals 6 to t equals 0. So if we were going to write this all up, it would look something like this. What we're getting is total snowfall accumulation in inches over that 6-hour period. So notice again that rate of snowfall is our rate of change. T equals 0 to t equals 6 is the interval that we are looking at this. And then total snowfall accumulation, that is what represents our net change. That is the net change portion in this description up here. All right, so let's look at another example that will actually have you guys plugging in some numbers. So let's look at this one, okay? We got, read this problem right here and see if you can figure it out. You will need to use FNINT to solve this, so make sure you got your calculators ready and give it a shot. Okay, if you tried this, well, how would we find a change in position? Because really, we're given an initial position of 11 feet at time t equals 0, but we want what the position is at t equals 4. So this is something that I'm going to write down right here, which will help you guys out a lot when you're solving kind of more real-world applied problems using integrals like this. Think about this, that a final value of something is always going to be equal to the initial value plus the change. And again, if an integral represents a net change, this portion right here is going to be the integral. So if we want, let's say, x of 4, that will be equal to x of 0 plus the integral from 0 to 4 of v of t dt. Okay? Now look what happens if we rearrange this equation. If we move that x sub 0 over to the other side, we just get the integral from 0 to 4 of v of t dt is equal to x of 4 minus x of 0. And doesn't that look very familiar to what we saw on the previous slide, where we had the integral of the rate of change gives us the net change? So in this case, velocity is the rate of change of position. So therefore, the integral of the rate of change of position will give net change in position. All right? So if you went through and plugged this in, you should have gotten that the initial position was 11 feet. So we'd have this would be equal to 11 plus, if you plugged in this integral using FNIT in your calculator, you should have gotten 0.49, which would make this 11.49. If you didn't get this, one thing I would suggest is check your calculator. Make sure you are in radian mode and not degree mode, because we always use radian mode when we're in calculus. If you guys hear that bass sound that's going on right now, maybe you can't. I'm actually recording this video while you guys are having your snowball dance, and that is in no way depressing.